Get ready, everybody, because we're about to dive into a paper all about Lie groups and homogeneous spaces. And there's this really cool thing called sharpness
Yeah.
that we're going to be looking at, too.
So what we're really trying to dig into with this paper is how these groups of transformations, these sort of symmetries, how they actually interact with spaces that are already kind of, really symmetrical themselves.
Okay, so before we get too far into it, maybe we should take a step back. What exactly is a homogeneous space? I mean, is it something like, I don't know, like a sphere?
You're totally on the right track. A sphere is a perfect example. Every single point is basically the same as any other. It's got that perfect symmetry.
Yeah.
You could also think about like a torus, that donut shape,
Yeah.
that also have that kind of consistency, that symmetry.
So it's not just theoretical shapes then. These homogeneous spaces, they have real-world connections.
Yeah, for sure. They pop up all over in math and physics.
Okay, that's super interesting. But what about these Lie groups? Where do they fit in?
Think of Lie groups, kind of like the rule makers, right? They're these groups of transformations, and they're acting on our homogeneous spaces.
Yeah.
A simple way to think about it maybe is imagine you're rotating a square, right? That rotation, that's a symmetry, and we can actually describe it using a Lie group.
So then these groups, they're kind of helping us figure out the underlying structure of these spaces, right?
Exactly. They give us these tools, right? This whole new way to describe and analyze things.
That's pretty cool.
Yeah, and it's not just about the shapes themselves or the groups. It's about what we can learn from them. These properties, these symmetries, they end up impacting tons of other math, leading to all sorts of new discoveries.
That's wild. Okay, so this is where things start to get really interesting, for me at least. The paper introduces this whole idea of sharpness. What does that even mean in this context?
All right, so imagine, you've got this group, right? And it's acting on a space. Kind of like, moving pieces on a chessboard.
Yeah.
But obviously, way more dimensional.
Okay, I think I'm with you.
So sharpness is basically describing how this action spreads out in that space.
Yeah.
If it's sharp, it means it's not all clumped together,
Yeah.
It's avoiding certain areas and spreading quickly and evenly.
So it's like it's trying to cover as much ground as possible without getting bunched up?
Yeah, exactly.
Okay, so how does this conjecture that the paper proves play into all of this?
Right, so the conjecture, it basically says that if you've got this group action and it's properly discontinuous, meaning it's not clustering up, and it's also cocompact, meaning it covers the whole space without leaving any gaps, then that action has to be sharp.
So if it's already spread out and avoiding those crowded areas, it's got to be sharp.
Exactly. It's kind of intuitive when you think about it that way.
It is, yeah. But why is the sharpness thing such a big deal?
Well, that's the million-dollar question, right?
I guess so.
It's not just some random property. Sharpness, it's like this bridge, and it connects us to this whole other area of math called Anosov representations.
Anosov representations. Okay, now you're just using big words to sound smart.
No, but they are really cool, I promise.
Yeah, okay, I'm listening.
So imagine these really special, really rigid ways of representing groups.
Okay.
But instead of just any transformations, we're talking about transformations of hyperbolic spaces.
Hyperbolic spaces, right?
Yeah. Think of them like spaces with negative curvature.
Like the surface of a saddle.
Exactly. So Anosov representations, they're like these maps. But instead of showing us physical places, they show us how these groups are transforming and distorting these hyperbolic spaces.
Okay, so sharpness is our bridge to understanding these Anosov representations within hyperbolic spaces.
We got it.
That's pretty cool. But I'm still not quite sure I understand. What's so groundbreaking about this connection?
So the paper, it shows this incredible link.
Yeah.
It says that in certain cases, if the action of a group on a homogeneous space is sharp, it actually implies that the group can also be represented as an Anosov representation.
Whoa, hold on. So we learn about one thing, this sharpness, and it unlocks all this information about something totally different, these Anosov representations.
Exactly. It's like finding the secret passage between two rooms.
That's amazing. So what are the implications of all of this? What can we actually do with this knowledge?
It's huge.
Yeah.
It means we have this whole new set of tools for studying groups. Just by understanding their sharpness properties, we can start using tools and techniques from the world of Anosov representations to learn even more about them.
So it's like getting a new pair of glasses that helps us see these mathematical objects in a whole new light.
Yeah, exactly. It's like upgrading our toolkit,
That's incredible. I'm starting to see why mathematicians get so excited about this stuff. It's like this whole hidden world of connections and patterns.
Absolutely.
But I have a feeling we're not quite done with this mathematical adventure yet, are we?
You're right, there's more.
Okay. What else does the paper dive into?
So remember how we were saying that some of these homogeneous spaces, they're like those perfectly symmetrical shapes? Yeah, yeah.
Well, it turns out that not all of them can actually be folded onto themselves to make those nice compact spaces. Like if you imagine folding a piece of paper into a perfect cube.
So some of them are just too, like, wild to be tamed into that compact form.
Yeah, exactly. They just resist that kind of folding no matter what you do.
That's kind of hard to wrap my head around, honestly.
It is pretty mind-boggling.
So then how does this sharpness idea come into play here?
Well, the paper actually uses sharpness to prove that certain homogeneous spaces just can't be folded that way.
So it's like sharpness helps us see which spaces can be neatly organized and which ones just won't cooperate.
Exactly. It's like it gives us this X-ray vision into these really complex structures.
That's pretty wild. Does the paper give, like, specific examples of this? Oh, yeah, definitely. There's a whole table of them, actually. Table 3, I think. And it's really interesting to see the range of cases they cover. Like, one of them involves this homogeneous space that's connected to a specific group of matrices. And using their results about sharpness, the authors show that this space just cannot be folded into a compact form. It would be like trying to fit a square peg into a round hole, you know?
So the structure just fundamentally doesn't allow it.
Exactly.
That's fascinating.
It is. But then the paper takes it even further. They start looking at a specific type of homogeneous space called group manifolds.
Group manifolds.
Yeah, so basically we're taking those Lie groups we talked about and looking at them as spaces themselves.
So we're going even deeper into Lie group territory.
Pretty much. And here's where it gets really interesting. The authors, they think that all the stuff we've been talking about sharp actions and Anosov representations, they think it might actually hold true for even more general types of homogeneous spaces.
Whoa, wait, so all these connections we've been making, this might just be the tip of the iceberg.
That's what they're suggesting.
That's a pretty bold claim.
It is. And if it's true, it could completely change how we understand these mathematical objects.
So this paper, it's basically opening up a whole new world of possibilities for mathematicians.
Exactly. It's like a call to adventure, you know?
Go forth and explore these uncharted mathematical territories.
That's the spirit.
Well, on that note, I think we've definitely given our listeners a lot to think about today.
I hope so.
We started with this idea of sharpness and ended up on this wild ride through homogeneous spaces, Lie groups, Anosov representations. It's amazing to see how these seemingly abstract mathematical concepts can lead to such incredible discoveries.
It really shows you the power of math, right?
It really does. And it makes you wonder what other mathematical mysteries are still out there just waiting to be uncovered.
Oh, I'm sure there are plenty. That's what makes it so exciting.
That's the beauty of it, right? There's always more to learn and explore. Well, that's all the time we have for today's deep dive. Thanks for joining us, everyone.
Thanks for having me.
Welcome back for another deep dive. Ready to get those brain juices flowing?
Absolutely. Always up for a good mental workout.
Okay, good, because today we're taking on this sharpness of proper and cocompact actions on reductive homogeneous spaces.
Whoa, that's a mouthful.
Yeah.
Sounds a bit intimidating, right?
Just a tad, yeah.
It-
But hey, I'm always up for a challenge, especially if we can uncover some hidden mathematical treasures along the way.
You got it. And trust me, this one's got some real gems. The core ideas here are surprisingly intuitive once you get past the jargon.
All right, you've got my attention. So where do we even begin with a title like that?
Let's start with something everyone can relate to. Imagine you're trying to understand the shape of the universe.
Okay, going big right off the bat. I like it.
But instead of a vast empty space, picture it covered in these repeating patterns. Kind of like a mosaic. It goes on forever, infinitely.
Okay, I'm kind of seeing it like those crazy intricate tile patterns you see in like Islamic art, but on a cosmic scale.
Exactly. You're picking it up fast. And the way those patterns connect, those repeating chunks that make up the whole thing, those are what mathematicians call compact quotients.
Compact quotients. Okay, I'm trying to file that away in my brain.
Think of it like this. You're taking something infinitely big and finding a way to represent it with a small, well-defined piece.
So, like, a single tile can tell us something about the entire infinite pattern.
Exactly. And this idea, it fascinated mathematicians over a century ago, folks like Poincaré, a real giant in the field. And this paper, well, it's picking up that torch, exploring how these tiles, these compact quotients, fit together, especially in a very specific way.
So we're talking about a legacy of exploring the very fabric of the universe through mathematical patterns.
That's a great way to put it. This paper tackles something called the sharpness conjecture, which delves into the very specific rules governing how these tiles can be arranged.
Okay, sharpness conjecture. I'm taking notes here.
But to really get into that, we got to step into the world of homogeneous spaces.
All right, lead the way. What exactly are these homogeneous spaces, and how do they connect to these cosmic tiles we're discussing?
Okay, so picture, if you will, a perfectly smooth sphere. Now imagine you can rotate that sphere, spin it every which way you can think of.
All right, I'm with you so far. Got my imaginary sphere spinning.
Now the key here is that every single point on that sphere, it's basically the same. There's no special point. Everywhere is essentially identical. That's what makes it homogeneous.
Okay, so no matter where you are in the sphere, it all looks the same. Got it.
And those rotations, those transformations we're doing, they form a group. And the sphere itself, that's our space that this group is acting upon.
Okay, so the sphere is our space, and the rotations are a group acting on it.
Gotcha.
So how does this tie back to those tiles, those compact quotients? Do we get to, like, slice and dice this homogeneous sphere?
That's exactly where we're headed. We want to divide this homogeneous space, our sphere in this case, into pieces. And yep, those pieces, mathematically speaking, are called quotients. You can think of them as our tiles.
So we're tiling our sphere. Got it.
And just like tiling a floor, we want these tiles to fit together perfectly. When we piece them back together, they should give us back our original sphere. But of course, there are rules to this mathematical game.
Oh, there are always rules in math, aren't there? So what are the rules for making these perfect mathematical tiles? Fill me in.
First rule, just like tiling your bathroom floor, no overlaps. Each tile sits right next to its neighbor, nice and snug, no overlapping. Mathematicians, they call this proper.
Makes sense. Got to keep things tidy. What's rule number 2?
Rule 2, we need clear boundaries between our tiles. No smushing them together. They got to be distinct. That's discontinuous.
Okay, so proper discontinuous. We're building this mathematical tiling project step by step.
Yeah.
What's the final rule we got to follow?
All right, last rule, we got to be able to cover the whole A&E sphere using a finite number of tile shapes. We don't want to be messing around with an infinite number of crazy shapes that gets messy.
Yeah.
We want to keep things manageable. That's cocompact.
Cocompact. Got it. So to recap, our mathematical tiles got to be proper, no overlaps, discontinuous, clear boundaries, and cocompact, meaning we use a limited number of shapes to tile the whole space. But we were talking about sharpness, right? How does this sharpness idea fit into our tiling project?
Sharpness. This is where the analogy gets really interesting. Imagine, right, that the shape of our tiles actually changes as we move further and further away from a specific point on our sphere.
Whoa, hold on. Changing tile shapes, that's next level tiling. I gotta hear more about this sharpness thing.
So basically, sharpness means that certain groups of transformations, remember those rotations we talked about? Those rotations will always lead to this very specific kind of bizarre type of tiling where the shape of the tiles is directly related to how far away they are from a central point.
So it's not just about the tiles fitting together, it's about how they fit, how they change as we move through the space. My brain's doing backflips trying to picture this.
It's some pretty wild stuff. But here's the kicker. What makes this sharpness so important is that it gives us this whole new toolkit to understand how these homogeneous spaces, these mathematical structures, actually behave. It's like finding a hidden code that unlocks a deeper level of understanding.
So sharpness is like a secret decoder ring for the mathematical universe. That's amazing. But how does this theoretical stuff translate to the real world? What are the practical implications of this sharpness concept?
Oh, the implications are huge. This research has big consequences for fields like spectral analysis.
Spectral analysis. Okay, you're going to have to break that one down for me.
Yeah, give like this. Imagine you're using sound waves to map out a hidden chamber. You analyze how the waves bounce back, and that reveals the shape of the room.
Okay, so we're using sound to see in the dark, basically.
Exactly. And spectral analysis in mathematics is kind of similar. It helps us study the structure of complicated spaces, even those super weird non-Euclidean ones, by looking at how certain waves or functions act within those spaces.
So instead of sound waves, we're using mathematical waves to explore hidden dimensions and structures.
You got it.
That's mind-blowing. Okay, but how does sharpness fit into all of this?
Sharpness is key because it gives us a precise way to understand how these waves are affected by the geometry of the space they're traveling through. It's like knowing how the shape of a concert hall affects the way the music sounds.
So sharpness helps us fine-tune our mathematical hearing in a way, letting us understand these spaces with more precision.
Exactly. And the more we understand how these spaces work, the more potential applications we uncover. Like, This research on sharpness has some pretty fascinating implications for something called openness of actions.
Okay, openness of actions. You're going to have to unpack that one for me too.
All right, so imagine you have this perfectly balanced structure and you give it a little nudge, just a tiny one. Sometimes that nudge can set off a chain reaction, completely changing the whole structure.
Like a domino effect, right? A small change creating a much bigger impact.
Exactly. But get this research is showing us that in certain mathematical structures, even if you give them a nudge, they stay stable. They can handle change without falling apart.
Whoa, so they're like super resistant to change, like they've got built-in shock absorbers or something?
That's a great way to think about it. They can bend without breaking. And this stability is a big deal because it helps us see how strong, how robust these mathematical objects are.
Okay, so we've got sharpness helping us understand how things work in these spaces, and now we see that sometimes these spaces are surprisingly resilient to change. This is pretty mind-blowing stuff.
It is. And it doesn't stop there. There's another fascinating consequence of this research, something called non-existence of compact quotients.
Non-existence of compact quotients. All right, you're gonna have to walk me through that one because my brain's starting to hurt a little.
Okay, remember how we talked about tiling the sphere, right? Well, this research actually proves that for some spaces, no matter what you do, you just can't create a tiling that follows all the rules, proper, discontinuous, cocompact, using just a finite number of tile shapes.
So it's like trying to fit square pegs in round holes. It's just not gonna happen no matter how hard you try.
You got it. It's mathematically impossible. And proving that impossibility, that non-existence, is a huge deal in mathematics. It tells us something fundamental about those spaces, about what they can and can't be.
So it's like drawing boundaries in the mathematical world, defining the very limits of what's possible.
Exactly. And, this paper, it doesn't just stop at the theoretical level. It dives into a very specific type of homogeneous space called group manifolds.
Group manifolds. All right, now we're getting into some seriously advanced math here. What are group manifolds and why are they so special?
Remember how we talked about those transformations, those rotations that act on our space? Well, imagine taking a whole bunch of those transformations, and instead of thinking of them as actions, you think of them as points themselves. Now, we can try to tile this space of transformations using copies of itself. And that, my friend, is essentially what a group manifold is.
Okay, you lost me a bit there. We're tiling transformations with more transformations. It's like a hall of mirrors, but with math.
It definitely takes some mental gymnastics to wrap your head around, but trust me, it's some elegant math. And here's the kicker. The authors of this paper, they actually cracked a specific case study with these group manifolds, what's known as the A2 case.
So they solved a piece of the puzzle, a piece of this group manifold mystery. What did they find out?
They found that in this A2 case, the only way to tile the group manifold is actually pretty simple, very predictable.
Simple in math. That almost sounds disappointing, like it's not complex enough to be interesting.
I know, right? But here's the thing. Even though the answer might seem simple, it leads to a ton of new questions. It's like opening one door and then realizing there's a whole hallway of more doors behind it.
So it's less about the destination and more about the journey, the new paths that this simple solution opens up.
Exactly. And that's what makes this research so exciting. It's not just about the answers we find, but the new questions, the new mysteries that emerge along the way. It's like we've just dipped our toes into the ocean of group manifolds, and we're already seeing these incredible patterns emerge. But there's so much more to explore. Like, one of the big mysteries is what happens when we move beyond that simple A2 case.
Right, that A2 case, it felt like we were working with a kind of mathematical mirror, where flipping things around didn't really change anything.
Exactly. That's because the A2 case deals with a specific type of symmetry. But most group manifolds, they're not so straightforward. They don't have that same kind of symmetry, which makes understanding their tilings, their compact quotients, way more challenging.
So it's like trying to solve a jigsaw puzzle, where the pieces keep changing shape on you.
That's a great way to put it. It's a real head-scratcher for mathematicians. But even though it's tough, this paper, it doesn't leave us completely in the dark. The findings, especially what they learned from that A2 case, they've led to a really interesting conjecture.
A conjecture. Ooh, I love a good mathematical mystery. So what does this conjecture suggest? What are we thinking about these more complex group manifolds?
Well, the conjecture proposes that for these more complex cases, any tiling, any compact quotient we try to create, it's going to inevitably break down into smaller, more manageable pieces.
So instead of trying to tackle the whole complex structure at once, we break it down into bite-sized pieces, a divide-and-conquer approach to these mathematical giants.
Exactly. Makes sense, right. And the hope is that by studying these smaller, more digestible parts, we might start to see the bigger picture, the overall structure of these more complex group manifolds.
It's like those Russian dolls, right? You open one up, and there's another one inside, and another one inside that. Each layer holds a clue to the whole thing.
I love that analogy.
Yeah.
And just like those dolls, the beauty is in the unfolding, the discovery of each intricate layer. We might not have all the answers yet, but this research gives us a glimpse into the incredibly intricate and often counterintuitive world of group manifolds.
That's what I love about these deep dives. We start with something that sounds incredibly complex, but as we break it down piece by piece, these hidden patterns, these beautiful mathematical structures, they start to emerge. It's like we're uncovering a hidden language, a code that underpins the universe itself.
Absolutely. And the best part, we're just getting started. There are so many more questions to ask, so many more layers to peel back.
And who knows what incredible discoveries lie ahead. Maybe one of our listeners will be the one to crack the code of these complex group manifolds or uncover a whole new mathematical mystery waiting to be solved.
Now, wouldn't that be something?
It definitely would. Well, on that note, I think we've done our brains a good workout for one day. Big thanks to you for diving into this complex topic with me and for making it so understandable.
Anytime. Always happy to geek out about math.
And to our listeners, thanks for joining us on this deep dive into the fascinating world of sharpness of proper and cocompact actions on reductive homogeneous spaces. Until next time, keep those minds curious, and we'll catch you on the next deep dive.
Okay, so have you ever just looked at like those intricate tile patterns? You know, the kind, I mean, like the ones you might find in like Moorish architecture. You know how they seem to just like go on forever and they're always like perfectly interlocking?
Yeah, totally.
It's pretty amazing. Well, just imagine trying to like create those patterns, but instead of working on a flat surface like a floor or a wall, you're working on this like mind-bending, like infinitely vast mathematical space.
And it's not even just like pretty shapes you're working with either. It's like these tiles are generated by the actions of mathematical groups, you know, like you're shifting or reflecting some basic unit over and over and over again. And
Wow.
yeah, it gets kind of wild. And so like figuring out when you can like seamlessly tile these really complex spaces, like mathematicians have a name for it. They call them compact quotients. And it's been a really intriguing problem for mathematicians for ages, really.
So it's like we're trying to understand the underlying blueprint, like the blueprint that even allows for these like perfect infinite patterns to exist at all.
Exactly. You got it. That's a great way to put it. And it turns out, I mean, this is where it gets really interesting, is that things get really interesting when the tiles, those shapes that we're working with, when they're based on what mathematicians call noncompact groups. And these are, well, they're groups where the elements can kind of like, in a sense, stretch out infinitely.
We've gone from tiling floors to like navigating infinite mathematical landscapes. Basically, yeah.
So where does this whole sharpness idea come in? Good question. Yeah, so sharpness. Sharpness is, it's like this property that mathematicians, they suspected that it was key, really, to creating these compact quotients, but it's like it only works in certain spaces, you know what I mean? And it's, how do I explain this? It's basically like a way of measuring how a subgroup, and think of a subgroup like a smaller nested pattern within our tiling.
Okay.
It's a way of measuring how that subgroup kind of like sits within a larger group.
So how do you even measure how a subgroup like sits inside a larger one? It's like we can pull out a ruler. Sure.
Yeah, no, you're right about that. We definitely need more sophisticated tools than that. Okay, so imagine this. Imagine like, you know how map makers, they have to project the Earth's sphere, which is round, right, onto a flat map.
Right.
So they use a projection to kind of translate points from one space to another.
Mm-hmm.
Mathematicians, we do something, well, it's kind of similar, right? We use something called the Cartan projection. And it basically allows us to take elements of our groups and kind of map them onto a different space, a space that's easier to work with, a space where we can actually analyze them.
So it's like giving us a new perspective,
Right.
like a way to visualize these groups and how they relate to each other that's actually like doable.
Precisely. Yeah, you got it. And so now sharpness, In this context, with this Cartan projection thing, sharpness means, well, it means that the Cartan projections of the elements from our subgroup, they diverge from the projections of like another fixed subgroup. But, and this is important, they diverge in a very specific way. They escape linearly, is how we describe it.
They escape linearly?
Yeah, it's like, okay, imagine like two hikers, right?
Right.
And they're on paths, and those paths, they diverge, they steadily move away from each other.
I see.
And that's kind of what these projections are doing. They're moving steadily away from each other. And that's what makes sure that the tiling doesn't overlap. That's what sharpness is ensuring.
So instead of like meandering all over our mathematical landscape, these projections are like staying on their paths, and that's how we get those tiles to fit together perfectly.
Yes. You got it. That's exactly it. And that's crucial for this whole idea of proper discontinuity is what it's called, which basically just means that no two tiles overlap.
Which makes sense.
Right, which is essential. It's a requirement for a compact quotient. And so the really exciting thing is that there's all this like recent research that's actually proven this long-standing hunch that mathematicians have had about sharpness. So what was once just the sharpness conjecture is now an actual theorem.
Okay, now this is where I really perk up. A proven theorem.
Mm-hmm.
So we're not just talking about like abstract ideas anymore. This has actual concrete implications, right?
You got it. Absolutely.
So this fundamental ingredient idea is really clicking with me. But you hinted at this earlier. It's not just about what we can do with sharpness. It's also about what we can't do, right?
Yeah, that's a really good way to put it.
It's like this theorem is revealing like these invisible boundaries in the mathematical world.
Exactly. Sometimes in math, proving something cannot exist is just as enlightening as proving that it can. And sharpness gives us the tools to do that.
Okay, so can you give me like a concrete example of that?
Sure, absolutely. Let's look at a specific type of space. Okay, it's denoted as SO2, 2K plus 1 U1K. And now K, that's just a positive integer.
Okay.
So don't get too bogged down in the notation or anything.
Mm-hmm.
Essentially, this represents a whole family of spaces, and they have increasingly complex structures as you go. But what sharpness helps us prove is that you simply can't create those perfect compact tilings in these spaces.
It's impossible.
It's mathematically impossible, yeah.
Wow. So even with the sharpest tools, some doors remain like firmly closed. We can actually prove that certain mathematical structures just cannot exist.
Right.
It's kind of mind-blowing when you think about it.
It is, and it actually has this ripple effect, on other areas of research. So, for example, confirming that compact quotients just can't exist in these cases, it helped to solidify a conjecture by a couple mathematicians.
Oh.
And wit.
Okay.
Their work was exploring which subgroups, within a larger family, so these are subgroups within SO2, 2K plus 1, which ones allow for those compact quotients and which ones don't. And sharpness, well, it provided the key to like unlocking that puzzle.
So it's like we found this missing puzzle piece, and it not only completes one picture, but it's like there's a hidden message on the back.
I like that analogy a lot. And those hidden messages, those can lead us to even more fascinating discoveries. So remember how we were talking about sharpness helping us understand whether like warped tiles would still fit together?
Right.
Well, that relates to the stability of these compact quotients. So imagine you take a space that's perfectly tiled and then you deform it just a little bit.
Okay.
Sharpness can help us determine if those deformations would completely ruin the pattern or if the tiles could somehow like readjust to maintain a compact quotient.
So it's like testing the resilience of our mathematical patterns. Like, can they withstand a little bit of pressure?
Exactly. And what's even more fascinating is that sharpness, it actually has connections to areas of math that seem completely unrelated.
Okay, like what?
Like Anosov representations.
Anosov representations.
Yeah, have you heard of those?
I can't say that I have.
Okay, so Anosov representations, they're kind of a way to understand how we can represent groups using matrices.
What?
And these matrices, they capture the group's essential properties. These representations are really interesting because they're what we call well-behaved. They exhibit this kind of like stretching and contracting behavior that's actually kind of similar to what you see in chaotic systems, but with this like really beautiful underlying order.
Okay, I'm definitely intrigued, but I'm also having a little trouble picturing how this all ties back to our tiling problem.
Yeah, I get that the connection might not be immediately obvious, but here's the gist. Sharpness, it acts like a bridge between the geometry of our tiling problem, with those homogeneous spaces and compact quotients, and it connects that to the algebraic world of Anosov representations.
Yeah.
It turns out that if certain Anosov representations exist, Well, that can actually guarantee that compact quotients with specific properties also have to exist.
So we're saying that these areas of math that seem totally different, tiling group representations, even chaotic systems, they're all connected in a way that we're only just beginning to grasp.
Precisely. And it's through these really powerful tools like Sharpness that we can even start to unravel these connections and begin to explore like the true depths of these mathematical landscapes.
It makes you question everything you thought you knew about math.
It really does.
But before we get totally lost in the mathematical weeds here, you mentioned that there's even more to this Sharpness story, something about compactly generated subgroups.
Oh yeah, you're right. There's another layer to this. So the initial sharpness conjecture that we've been talking about, it focused on discrete subgroups. So those are the ones with like distinct separated elements.
Right.
But it turns out that sharpness, it actually holds even for more general subgroups, ones that are compactly generated.
Okay, so before we get into that, can you give us like a quick, accessible explanation of what compactly generated actually means in this context?
Sure. So imagine you're trying to cover a really large area with a set of shapes. If your shapes are compactly generated, it means you can create any shape in your set by like combining a finite number of copies of some really basic bounded shapes.
So it's like having a finite set of tools, but you can build an infinite number of structures with them.
You got it. And this idea of generalized sharpness, this applies even to these compactly generated subgroups. And it has some pretty amazing consequences. For example, it tells us that if a homogeneous space has a compact quotient, well, then the subgroup involved has to be both compactly generated and what we call quasi-symmetrically embedded in the larger group.
Whoa, okay, hold on a second. There are a lot of really big words being thrown around right now. Can you break it down for me? What's the significance of this?
It's kind of like a two-for-one deal.
Yeah.
So not only does sharpness help us to find those perfect tilings, but it also tells us something really fundamental about the actual groups involved.
Right.
This quasi-isometrically embedded part. What that means is that the subgroup, when we look at it through the lens of large-scale geometry, it actually looks really similar to the larger group that it's sitting inside.
So it's like the subgroup inherits some of the essential geometric properties from its parent group.
You got it. Exactly. And these insights, well, they can lead us to even more unexpected discoveries. So, for example, let's take the world of what we call group manifolds.
Group manifolds.
Oh.
This deep dive is just getting more and more intriguing. What are group manifolds?
Okay, so imagine this. Instead of tiling a floor, we're now sculpting. Sculpting with a snake. And this snake, it's constantly moving and it's infinitely flexible.
Okay, I'm officially lost now.
Right.
We've got snakes, we're sculpting. What's going on?
Okay, bear with me here. So a group manifold, it's basically this fascinating space where you consider a Lie group, and that's just a special type of continuous group that has some really nice properties, and we consider this group as a homogeneous space under its own action.
Okay.
So picture our snake, right? It's constantly shifting and changing, but somehow it still forms this stable, coherent shape, and that shape, well, that represents the group manifold.
Okay, so I think I'm starting to wrap my head around this whole like constantly shifting snake and this group manifold thing.
Yeah.
But where does sharpness come in? Like, how does it apply to this already very strange landscape?
So sharpness basically helps us to untangle the snake.
Okay.
It lets us understand the structure of compact quotients. And remember, those are like the perfectly tiled portions within these group manifolds that are constantly changing and moving around.
So instead of tiling a floor, we're trying to tile something that's constantly moving and changing shape.
Yeah, basically.
That sounds like quite a challenge.
It is, but it's also incredibly rewarding. Let's take an example here. Okay, so let's take a real simple Lie group.
Right.
Okay, and let's say it has a restricted root system of type A2.
Okay.
Now, I know that sounds complicated, but just try to visualize it as like a specific species of our infinitely flexible snake. Okay, this one moves and changes in a very particular way.
Okay, so I'm picturing a snake with like a very specific slithering style.
Exactly.
So what happens when we try to apply sharpness to this, like to understand those compact quotients, those tiled sections, but within this A2 snake?
So sharpness is telling us that if there is a discrete subgroup, so think of that as like a specific pattern within the snake scales.
Okay.
If there's a discrete subgroup and it's acting properly, discontinuously, and co-compactly on this group manifold, well, then that subgroup has to have a very, very particular form.
So it's like saying that only certain scale patterns are actually compatible with the snake that can only move in this A2 way.
Exactly. It's like the snake's movement is actually restricting the possible arrangements of its own scales. And these restrictions, these are all dictated by sharpness, and they give us incredibly deep insights into the structure of these group manifolds and their compact quotients.
This is incredible. We've gone from tiling floors to to grappling with infinitely flexible snakes and their scales, and it's all thanks to this idea of sharpness. What a journey this has been.
And this journey, well, it's far from over. Remember those limit cones we talked about earlier?
Right, those shapes that we get when we view our tiles from like infinitely far away.
Exactly. Well, they play a really crucial role in this research too.
Okay, I'm sensing another one of those, but wait, there's more moments here.
Chuckles. There's always more to explore.
So how do limit cones fit into this whole picture of group manifolds and sharpness?
Well, when you apply sharpness to group manifolds, it's like it gets deeply intertwined with the geometry of those limit cones. Essentially, sharpness is making sure that the limit cones that are associated with the subgroup and the fixed subgroup, it's making sure that those are well separated, that they don't overlap, they don't intersect in any way that would cause problems.
Okay.
And that's really important for those compact quotients to even exist within the group manifold.
So for our snake, for it to have those beautifully tiled sections within its constantly changing form, its limit cone, whatever that looks like,
Yeah.
that also has to have certain properties, and those are all dictated by sharpness.
You got it. And so this connection between sharpness and group manifolds and limit cones, it's marked a whole new wave of research. Mathematicians are now seeing if they can use these tools to classify certain types of group manifolds to figure out their fundamental building blocks and to really pin down exactly when those compact quotients can exist.
It's like we've been given this brand new map, but it's a map to this vast, uncharted mathematical territory, and we're only just starting to explore it.
Exactly. And like any good exploration, this one's creating more questions than it answers.
Which I think is always a good thing.
Yeah. Can we develop even more precise tools to study these limit cones? What other connections are there? Connections between things that seem like they should have nothing to do with each other. Can we use sharpness to find those? These are the kinds of questions that really get mathematicians excited.
It's both exhilarating and humbling at the same time to realize how much we don't know.
Yeah.
But I think that's the beauty of math, right? This never-ending quest to learn more.
I think so too. And for anyone listening who's feeling inspired to go on their own mathematical exploration, just remember this. Every question, every connection that you make, no matter how small, it all contributes to our understanding of this really beautiful and honestly often very bewildering subject.
So keep those minds curious, keep exploring, and who knows what amazing discoveries are waiting out there for you. Until next time, happy exploring. Ever try wrapping your head around like the shape of the universe? Like it's just such a massive, crazy idea. It turns out mathematicians, they've got some pretty wild ways of tackling that. We're going to be diving into a paper today that deals with some seriously out there concepts, trying to get a grip on all of it.
Yeah, the title alone is a mouthful. It's called, get this, Sharpness of Proper and Cocompact Actions on Reductive Homogeneous Spaces.
Okay, gotta admit that sounds a little intimidating.
It's a mouthful, for sure.
Yeah.
But hiding behind all those technical terms, there are some seriously cool geometric ideas about how we can even begin to picture and understand these, well, complex shapes and spaces we're talking about, especially when we're talking about something as massive as the universe.
All right, so let's break it down a bit. Reductive homogeneous spaces. What are we talking about here?
Okay, think about it this way. Imagine a sphere, like a basketball. You know how no matter where you are on that sphere, it pretty much looks the same in every direction?
Yeah, totally.
That's the homogeneous part. Now, reductive, that's a bit more technical, but it basically refers to certain kinds of symmetries that these spaces have, which thankfully for mathematicians helps them narrow down what they're looking at.
Gotcha. So we're dealing with symmetrical spaces, but where does this whole sharpness conjecture thing come into play?
So this conjecture has been a bit of a brain teaser for mathematicians for a while now. It's all about how certain groups of transformations, ways to move things around actually behave when they act on these homogeneous spaces. Just imagine, say, you have a piece of paper, right?
Yeah.
And you can do all sorts of things to it. You can rotate it, flip it over, slide it around. All those actions, they form what mathematicians call a group. Now, the sharpness conjecture, this is the kicker, it makes predictions about how these groups will behave when they're let loose on way more abstract spaces, like those reductive homogeneous ones we mentioned, not just a simple flat piece of paper.
Okay, so instead of a flat piece of paper, are we talking about, like, picture a Pringles chip, that curved shape, and we're, like, moving it around in very specific ways.
Exactly. You're getting it. You've got a knack for this, you know? And the really interesting thing is that these researchers, they decided to test out this conjecture in a really specific, and let's be honest, unusual space, the three-dimensional anti-de Sitter space.
Okay, now we're just getting into some sci-fi stuff. Anti-de Sitter space. Gonna have to explain that one.
All right, so picture our universe, right? But instead of expanding outwards like it's doing now, imagine the fabric of space-time itself is curving inwards. It's kind of like, well, imagine a saddle shape that goes on forever in every direction.
Whoa, so like a universe where everything's constantly collapsing in on itself. My brain's already starting to hurt.
Yeah, it's a real mind bender for sure. But here's the thing, what these researchers found is that even in this warped inside out kind of space, this sharpness conjecture, it seems to hold true. And that has some potentially huge implications for how we understand gravity, especially in different dimensions. It's like, what if gravity doesn't always work the way we think it does?
All right, you've got my attention. Are you saying that by diving into the math of these bizarre spaces, we could actually uncover clues about the fundamental forces of the universe itself, like how gravity really works?
You're catching on quick. It's definitely a possibility. And this is where things get even more interesting, if you can believe it. This paper, it also dives into this concept called, get ready for it, compact quotients, which are, to put it simply, like finding these super clever ways to take complex geometric shapes and basically represent them in a more condensed form.
Okay, so it's like taking that infinitely curving saddle shape we talked about and finding a way to fold it up neatly, kind of like a map.
You got it. It's all about finding those elegant, neat representations of things that seem way too complex to even think about. And you know what? The researchers found that in some cases, it's actually impossible to do.
Wait, what? There are shapes that are just too complicated to be folded in that way. Give me an example. What kind of shape are we talking about here?
So they were looking at this space. It's represented by this, get ready, SLN, RSL, and RRR. I know, it sounds like a bunch of gibberish. But basically, imagine a space where you can like rotate things, shear them, stretch them, all in these super specific ways that are like determined by these things called matrices, you know? And it's for certain values of n, which basically just tells you how big these matrices are, how many dimensions they're working in, that they found you just can't squish this thing down into a compact form.
So no matter how hard you try, you can't fold it up without like ripping it or crumpling it,
Yeah.
right? What makes that such a big deal? What does it actually tell us?
Well, it kind of shakes things up a bit, you know? It really challenges our understanding of, like, the limits of geometry and topology. Topology, that's all about the properties of shapes that stay the same even if you stretch them or bend them. Like, remember that classic example? You can turn a donut into a coffee mug without, like, ripping or tearing it.
Yeah, I always love that one.
Right. So this discovery, it throws a bit of a wrench in some of those ideas we had about which shapes can be simplified topologically and which ones just can't. It's pretty groundbreaking stuff, honestly.
This is blowing my mind, honestly. Okay, so we've got these crazy shapes, we've got this mind-boggling conjecture, and now we're like rewriting the rules of topology. This paper is a wild ride, I'm not going to lie. There's got to be more, right?
Oh, there's more. All right. This paper, it also gets into this whole thing called, get ready for it, Anosov representations. Remember that ink drop in water thing we talked about?
Yeah, you said it's like finding hidden order in chaos, right?
Exactly. That's Anosov representations in a nutshell. They're like this bridge between systems that seem all random and chaotic and those that are more, you know, predictable, like clockwork. They're like these mathematical tools that help us see the patterns hiding beneath the surface of all the craziness. And what's really fascinating is how these researchers, they actually use Anosov representations to study these groups that are acting on these weird spaces, like that one that just refuses to be compactified, you know, the one we just talked about.
Okay, so instead of just saying, whoa, that shape is totally bonkers, it doesn't behave like anything we've ever seen,
Yeah.
Anosov representations, they actually give us a way to like study it, to understand it, right?
Exactly. You got it. They're like this secret decoder ring for the language of these crazy spaces. They help us understand how these shapes behave when we start messing with them, you know, with those transformations we talked about earlier.
That's incredible. Okay, but let's zoom out for a second. I know we've been deep in the weeds of all this mathematical craziness, but why should anyone listening even care? I mean, what does all this abstract math actually have to do with, you know, the real world?
That's the million-dollar question, right? Why should we care about any of this stuff? Well, it might seem like it's all theoretical, but trust me, this stuff has some surprising applications. Remember when we were talking about that anti-de Sitter space and how it might change how we think about gravity?
Yeah, that still has my head spinning a little, not gonna lie.
Well, the cool thing is what we learn from this research, especially how this sharpness idea and these Anosov representations all fit together, it could totally change how we understand gravity, maybe even help us finally figure out that whole theory of everything thing, you know?
Okay, now that's something I think everyone can get behind. Unlocking the secrets of the universe, that's pretty big.
Yeah.
But let's bring it down to earth for a minute. You mentioned real-world applications. Give me something a little closer to home, something we can all relate to.
All right, how about this? Computer graphics. Yeah, those crazy, realistic video game worlds we love to explore. Well, guess what? Anosov representations, they're being used right now to create better, faster algorithms for rendering those complex 3D images. So in a way, those awesome gaming experiences, they're built on the backs of these mind-boggling mathematical ideas.
No way. So this isn't just some pie-in-the-sky theoretical stuff. It's actually impacting things we interact with every day. That's wild.
You said it. It's impacting everything. And it doesn't stop there. We're also seeing Anosov representations popping up in cryptography, which means they're helping us create stronger, more secure ways to keep our digital secrets safe.
So we're talking about everything from the fabric of reality to, like, online banking. That's a pretty impressive range.
That's the thing about math. You never know where it's going to pop up next, but it just goes to show even the most out there, abstract stuff can have a huge impact on our lives, even if we don't realize it.
This deep dive has been a wild ride for sure, but we've covered a ton. Let's rewind for just a sec. I want to make sure we circle back to those compact quotients. Can you give us like a concrete example of how these researchers actually showed that certain spaces, they just can't be compactified? Let's dive back into those spaces that just refuse to be folded. How the researchers actually prove that's even a thing.
So they zeroed in on this one type of homogeneous space, and I'm going to try to say this without tripping over my tongue. It's represented by SLNN, RSLN1R. Bear with me. I know it looks like alphabet soup, but picture this. You've got the space where you can move things around, right? But you're not just rotating or shifting, you're stretching, squashing, all in these super specific ways, and it's all determined by these things called matrices.
I'm trying to visualize it. Keep going.
So the researchers, they showed that for certain values of n, and that just tells you how big these matrices are, how many dimensions they're working in, basically how complex the whole thing is, this space. You just can't cram it into a neat little package. No compact form for this one. It's like trying to stuff, I don't know, like an endless tablecloth into a tiny matchbox.
So no matter how much you try to fold it, twist it, cram it in there,
Yeah.
it's just not going to fit. It's fundamentally resisting being simplified.
Exactly. It really throws a wrench into how we think about shapes and spaces, you know?
Yeah.
We always assume, like, oh, with enough cleverness, we can find a simpler way to represent anything. But this research is like, nope, not so fast. Some spaces are just inherently too wild to be tamed that way.
It's like discovering a brand new law of nature, but for math. This whole deep dive has been incredible, honestly. We've gone from these abstract spaces to like maybe unlocking the theory of everything, even touched on video games and keeping our online secrets safe.
It really shows you the power of math, though, right? It's this amazing tool that connects all these seemingly unrelated things. It's like this hidden language of the universe.
Absolutely. So as we wrap things up here, what's the one big takeaway you want our listeners to walk away with?
I'd say never underestimate the power of a crazy idea. Even the most abstract, out there math can have these huge implications for, well, everything. This research is like this reminder that sometimes to make the biggest leaps, you got to dive headfirst into the unknown, no matter how weird it gets.
Love it. It's a universe full of mysteries, and sometimes the most mind-blowing discoveries come from exploring the most mind-boggling ideas. Thanks for joining us for this incredible deep dive. We'll catch you next time. Keep those brains buzzing.
Okay, so Lie groups. I'll be honest, sounds a bit intimidating at first glance. But hey, that's what this deep dive is all about, right? Especially with this paper by Kassel and Tholozan. Seems like we're in for a ride.
Oh, absolutely. And trust me, it's a fascinating area of math. You'd be surprised how often these, seemingly abstract concepts actually pop up in the real world.
Yeah, that's the thing about math that always gets me. Always more than meets the eye. So Lie groups, where do we even start? I need like a picture in my head,
All right, so imagine this. You're trying to tile an infinitely large bathroom floor, right? Some shapes, like your squares, your triangles, they'd work perfectly. But try doing that with, say, pentagons. You're going to have gaps, you're going to have overlaps.
Yeah.
Lie groups are kind of like those shapes, but instead of bathroom floors, we're talking about the very fabric of mathematical spaces.
Okay, I think I see where you're going with this.
Yeah.
So instead of like physical tiles, we've got these Lie groups acting as what? Building blocks within a space?
Exactly. They describe the continuous transformations, the symmetries within those spaces. And you know what? You're spot on about the spaces themselves. This paper focuses on some pretty unique ones, the homogeneous kind.
Homogeneous spaces, right? Yeah, I remember skimming that. But honestly, I need a refresher. What makes them special again?
So think of it like this. Imagine you're on a sphere, any point on that sphere. Your local experience, mathematically speaking, is the same everywhere, right? You can't tell if you're at the top or the bottom. It's all relative. That's the essence of a homogeneous space.
So a sphere, that's our homogeneous space. But wait, going back to our bathroom floor analogy, we were trying to tile those, right? How does that translate to, this Lie group world?
You're thinking like a mathematician already. That's where compact quotients come in. It's basically like finding a way to neatly fold up that infinite space into a finite, self-contained unit, as if we found the perfect tiling pattern. If we can do that, boom, we've got ourselves a compact quotient.
Okay, so it's not just about finding a old pattern. It's got to be like elegant, a perfect fit. But I'm guessing it's not that straightforward, is it?
You're catching on quick. It really depends on both the space itself and the Lie group we're working with. The shapes have to play nice.
Play nice, I like that. What makes them play nice, though? What are we looking for in these Lie groups?
It's all about something called properly discontinuous actions. Imagine stamping those Lie group shapes all over our infinite homogeneous space. Properly discontinuous basically means you can keep stamping away without any of your shapes overlapping.
Yeah.
And no infinite clumping allowed. Each shape needs its own space.
Got no messy overlaps, no overcrowding. Sounds familiar, like trying to organize my sock drawer. But speaking of things that can get messy, I've heard whispers of this Calabi-Marcus phenomenon. What's that all about?
Good point. Sometimes our Lie group shapes are just too similar to the space itself. It's like trying to tile a plane with, say, infinitely long, thin strips, and you'll never quite get a perfect cover. Calabi-Marcus tells us that in these cases, the only way to achieve a proper tiling, a compact quotient, is if we use a limited, finite number of those shapes.
So there are times when even in infinite space, some shapes are just too wild to make a neat pattern. Wild. But this paper, it goes beyond just Calabi-Marcus, right? There's this whole sharpness thing that caught my eye.
You're right, it does. The plot thickens, you could say. This paper dives into a really powerful tool for figuring out when we can actually achieve those nice tiled compact quotients. It's called the Sharpness conjecture. And get this, it's been proven.
A proven conjecture? Now, that's something you don't hear every day. So how does this sharpness thing even work? Is it like, I don't know, a mathematical ruler for Lie groups telling us if they're sharp enough for these compact quotients?
I like that analogy. Imagine this. We have a way to measure how far our Lie group shapes, as they're transformed by the group's actions, how far they move away from our original set. That's essentially what this thing called the Cartan projection does.
The Cartan projection. So we're like mapping things to a simpler space, making it easier to measure.
Exactly. It's all about getting a clearer picture of their movements, their behavior.
Okay, I'm with you so far. But how do we actually measure sharpness in this new space? What are we looking for specifically?
So sharpness, in this context, means that as our shapes are transformed, right, and they're moving around in the simpler space, they're doing so in a very specific way. They're escaping, going outward, quickly enough to avoid any collisions.
So it's not just about avoiding overlaps, it's about the speed, the direction of their movement in this mapped space. It's like they need to be sharp, decisive to create that neat tiling.
You got it. It's like a perfectly choreographed dance. Every movement is deliberate, preventing any awkward bumps or overlap.
That's a pretty cool way to think about it. But I have a feeling Kassel and Tholozan didn't just stop at proving the conjecture. They applied this to some real mathematical objects, didn't they?
You know it. And this is where things get really interesting, mind-bending even. They discovered that certain spaces, like this one, SLN, SLMR, for most values of n and m, they simply cannot be tiled with compact quotients, no matter what you do.
Hold on, are you saying there are shapes, mathematically speaking, that are just so wild, so untamable, that they can't even be contained within certain spaces? No matter how hard you try, gaps or overlaps are inevitable.
It's true. It really changes how we think about the very structure of these mathematical spaces, the kinds of patterns and structures that can even exist.
It's like, whoa, there are fundamental limits even in the world of mathematics in what we thought was an infinite playground of possibilities.
Exactly. And to make it even more intriguing, they highlight this specific case, SL4, SL3R, where this sharpness idea, it seems to be the only reason we know of for why compact quotients fail. It's a real head-scratcher, a true mathematical mystery.
Wow. So even with this powerful sharpness theorem, we still got unsolved puzzles in the mathematical universe. What other surprises did they uncover in this paper?
They also delved into the connection between sharpness and something called Anosov representations. Imagine, if you will, our tiles moving in a way that seems chaotic, random even, but there's this underlying order to it.
Chaotic, but in a good way. Controlled chaos.
Precisely. Turns out sharpness is closely linked to these representations in spaces of a certain rank, giving us a whole new perspective on their structure.
Chaotic in just the right way. I like that. It's like this beautiful dance between order and chaos, sharpness and flow. But for those of us who don't spend our days in the world of, higher mathematics, what's the takeaway here? Why should we care about these seemingly abstract concepts? So much to unpack here. Sharpness, Anosov representations, spaces that just refuse to be neatly tiled. It's a lot.
Right.
But for those of us who, don't live and breathe this stuff, what's the most practical takeaway here? What's the so what of all this heady math?
Well, believe it or not, this research actually has implications for other fields. Physics, for one, it sheds light on these things called pseudo-Riemannian locally symmetric spaces, which, yeah.
Okay, and in English that means?
Right, sorry. These spaces, they have this very specific type of geometry. It's actually crucial for understanding, well, the big stuff. General relativity, cosmology, gravity, space-time, how the universe evolves.
Whoa, okay, hold on. So we're not just talking about abstract mathematical spaces anymore. We're talking about potential insights into the fundamental nature of the universe.
Exactly. This sharpness theorem, all the concepts we've been discussing, they give us these new tools to probe the structure, the behavior of these spaces.
Yeah.
And that could unlock some really deep secrets about how gravity works, on a cosmic scale.
That is wild. It really is incredible how, I don't know, even the most abstract mathematics can have these profound ripple effects, it affects how we understand the physical world around us.
It really does. And that's just one example. I'm sure there are tons of other connections out there just waiting to be discovered.
It makes you wonder what other mathematical mysteries are out there just waiting to be, unraveled and to reveal even more about the universe. But before we get too far down that rabbit hole, was there, I don't know, any particular finding in this paper that really stuck with you? Anything that really made you go, whoa?
The case of SO2, 2K plus 1, U1K, that one really got me thinking. For certain values of K, this space, it just cannot be divided into compact quotients. No way, no how. It's like running into a bathroom floor that's impossible to tile no matter how many different shapes you try.
So there are spaces out there, even in the world of mathematics, where certain kinds of order and structure, they're just not possible. That's, I don't know, it's kind of frustrating, but also strangely beautiful at the same time.
It is. It makes you question, what are the underlying principles here? What's governing these limitations? What can these impossible tilings tell us about, I don't know, about the very nature of symmetry of structure itself?
Big questions, definitely something to ponder.
Well, I think we've given our listeners plenty to chew on today. It's not every day we get to explore the limits of tiling and what they might mean for, the entire universe.
It's been a good one. To everyone listening, if you find yourself suddenly dreaming about SO2, 2K plus 1, U1K, hey, you're not alone. It seems even mathematicians find themselves marveling at the spaces that defy our attempts to impose order. Until next time, keep exploring, keep questioning, and I guess keep those bathroom tiles firmly in place.